Hello everyone. In this video, we're going to start talking about how to do calculus with parametric curves. Now, if you think back to your first calculus class, one of the first things you did was define the derivative in order to calculate the slope of a function at a given point. So, our first goal will be to do the same thing for parametric curves. So how do we find the slope of a parametric curve at a given point? The answer is going to come from the chain rule. If x and y are functions of t, then the chain rule says that dy dt is equal to dy dx times dx dt. And now, if dx dt is not 0, we can rearrange this equation to get the dy dx, the slope of a curve at a given point, is equal to dy dt over dx dt. And now, a couple quick special cases. If dy dt is equal to 0 and dx dt is non-zero, then the fraction above is going to be equal to 0. And so the curve has slope 0 at that point, which means the tangent line is horizontal. On the other hand, if dx dt is equal to 0 and dy dt is non-zero, then the fraction above will be something like plus or minus infinity, which means the curve will have a vertical tangent line at that point. All right, so that's how we compute the first derivative, but what about the second? It turns out we can just plug dy dx in for y in the equation above, and we find that the second derivative of y with respect to x is equal to the derivative with respect to t of dy dx over dx dt. Again, assuming that dx dt is not 0. Now, let's apply these formulas to some examples. Consider the parametric equations x equals t squared and y equals t cubed minus 3t. First, let's find the equations of both tangent lines to the curve at the point 3, 0. Right away, this seems a little strange. What do we mean by both tangent lines? Well, it turns out the parametric equations can loop back on themselves and pass over a point multiple times. In this particular example, the curve looks something like this, where the crossover happens right at the point 3, 0. And since the curve passes through this point twice, you can see that we'll have two different tangent lines. So how do we find these tangent lines? The first thing we need to do is find the t values corresponding to the point 3, 0. If we set the x equation equal to 3, we find that t has to be plus or minus the square root of 3. Now, it's important that we plug these values into the y function to make sure we get the correct y value as well. But it turns out that the y value is 0 when we plug in both of these t values, and so we're all set. Next, we need to find the slopes of the tangent lines at this point. We're going to do that by using the equation we found at the beginning. We found that dy dx is equal to dy dt over dx dt. Taking the derivatives of our parametric equations, we get 3t squared minus 3 over 2t. Now, to find the slope of the two tangent lines, we plug in our t values, plus or minus the square root of 3, into this derivative, and we get that the slopes are also plus or minus the square root of 3. Finally, we can plug all of these values into point-slope form, and we get that the equations of the tangent lines are y equals square root of 3 times x minus 3, and y equals minus square root of 3 times x minus 3. As another example, let's try to find the points on this curve where the tangent line is horizontal. To do this, recall that the tangent line is horizontal when dy dt is equal to 0, but dx dt is not. In part A, we calculated that dy dt is equal to 3t squared minus 3. Setting this equal to 0, we find that t must be equal to plus or minus 1. Now, we must check that dx dt is not 0 at either of these t values. But we calculated that dx dt is 2t, which is not 0 when we plug in plus or minus 1, and so we're all set. So, we found the t values at which the curve has a horizontal tangent line. All we have to do now is plug in these points into our parametric equations to get the actual points on the curve, and we find that the tangent line is horizontal at the points 1, minus 2, and 1, 2. Next, let's do a similar thing, but instead find the points where the tangent line is vertical. This time, recall that the tangent line is vertical when dx dt is 0, but dy dt is not. We take dx dt, which we found to be 2t, and set it equal to 0. Solving for t, we get that t is equal to 0. As a check, we plug t equals 0 into dy dt and make sure we get something that's not 0, which turns out to be the case. So the curve has vertical tangent line when t is equal to 0. Plugging in t equals 0 into our parametric equations, we find that this corresponds to the point 0, 0. For the final part of this example, let's find when the curve is concave up and concave down. Remember, all of the information about concavity is contained in the second derivative of y with respect to x. We have a formula for this quantity that we found on the first slide, which tells us that the second derivative is equal to the derivative with respect to t of dy dx over dx dt. In a previous part, we found that dy dx is equal to 3t squared minus 3 over 2t. Simplifying this expression and taking the derivative with respect to t, we get 3 halves times 1 plus 1 over t squared, all over dx dt, which is equal to 2t. Finally, we can simplify this expression to get 3 times t squared plus 1 over 4t cubed. And now we want to know when this expression is positive and when it is negative. It turns out not to be too bad in this case, since the numerator is always positive. Therefore, the second derivative is positive when the denominator is positive, which happens when t is bigger than 0, and the second derivative is negative when the denominator is negative, which happens when t is less than 0. Thus, the curve is concave up when t is positive, and concave down when t is negative.